Ancestor of a binary size 3. Given a binary size 3, a BST, find the lowest common ancestor, LC, a node of 2 given nodes in the BST. According to the definition of LC on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. For example, in this one, root 6 is our current root node, and we have P as 2 and Q as 8. So 2 and 8, the lowest common ancestor is 6, and this one same 3, and we have 6 as our current root node, and 2 and 4 as our P and Q. And we have an output of 2 because our left child has to move to our to 2, since 2 is allowed to be a descendant of itself, and 4 is a descendant of 2, and our lowest common ancestor is 2, and that's why we have the answer. In example 3, similar to this one, 2, we have 2 and 1, and 2 is our root node, and 1 is a descendant of 2, and 2 is a descendant of itself. Our lowest common ancestor is 2. So in a BST 3, binary size 3, our left child is always smaller than its parent child, as you can see consistently, while our right child is always bigger than its parent child, as you can see also over here consistently throughout this tree. So that's how it is in a BST. So a time complexity in a BS3, a balanced tree, like in this case, is a log of n, and in a skew tree, it will be O of n. So let's see how we're going to do this. So let's make a while statement. While statement. So while we have a root, if let's assign our variables. A root value, let's give it root underscore value, root val, the val, and p underscore value will be assigned to our p dot val. So our q dot value underscore value, not value, given to q dot val. So let's make our conditions now. So if p is if the p value is less than our root dot value underscore value, and our q dot underscore value is less than our root underscore value, move it to the left. Let's move to our left child. So root dot left. So now let's make our root our left child node. So now else if, it will be the opposite of. So for example, this one applies in this case, in this example. So we have 2 and 4, which are less than the current node of 6. So we have to move to the left child of the current node of 6, and now we have this. So now we have it over here. So now let's make the opposite case of that. So L if p underscore value more than root underscore value, and q underscore value is more than root underscore value. Let's move it to the root dot underscore root that right child. So else, let's just give, if it doesn't meet any of these conditions, let's just return our root. And so let's get out of our loop, and if we don't have a root, we're not given a root to begin with, let's return let's return a root, a none. So move to the right child, if so. No, this is left child. Move to the left child if the the P and Q less than the current root node. This one will be left child, move to left child, and this one will be move to the right child. Move to the right child. Move to the right child. Right child. More than our current node. More. So now our size complexity stays at size complexity is O of 1, since no new space is being made. Let's run it and see if it works. Yes, and it's been accepted. And this is a good problem using binary size trees.